preload. It's something that you want in bearings to keep them from letting go. So what exactly is preload? Ever had a thing that moves and kind of rattles? Or a drawer that's kind of sloppy? Whereas other things move so nice and smooth. The ones that are nice and smooth moving all the time are typically preloaded. And what that does is, it's just like the word seems. You apply a load to something before you start using it, and you keep that load on it to give you steady, even performance. In terms of the mechanics of preload, it's also very interesting how things work as springs. Because remember, which I'm sure you have not forgotten, F equals Kx, everything's a spring. I have my little demonstration unit here. Here's a mass, and it's supported by springs. If this mass was, for example, a carriage that moved back and forth in a structure, the bearings would be like springs. Here you can see that both springs are under some tension. Even the lower one. The lower one is under some tension because if I were to unhook them, they'd both be shorter than where the position is the block, and then they're stretched and brought to the block. So when I move up and down, I feel how stiff this is. If I move such that the lower one spring is now loose, I'm applying a steady force to move the spring, but if I apply a little increment of force, I get it's a lot softer. Here, when I apply the same force, I get less motion. Indeed, when you work out the mechanics of F equals Kx for both of these springs, as long as both springs are in compression and they move such that the initial compression is never lost, the apparent stiffness of this block equals the stiffness of this spring plus the stiffness of that spring, even though one is in compression and one is in tension. It's a very magical result. What that allows you to do is start designing your machine to have these keeper rails or bearings supported by softer springs in series with bearings that are directly connected and very, very rigid to your carriage. So even though this bearing is on a soft spring and this bearing is now on a hard spring to the carriage has equal bidirectional stiffness, and that bidirectional stiffness is what you want for the outside of the carriage to be able to support a load and the machine to function as desired. But, for example, if the bearing rail that the carriage rides along has this manufacturing error, see it's got this droop in it, locally the soft spring supporting one of the bearing compresses, as shown here, and the carriage moves along nice and smooth and even along the bearing rail without feeling a tight spot. So the purpose of preload is twofold. The first is to give you bidirectional stiffness, equal bidirectional stiffness for uniform operation of your machine. It prevents any of this rattling motion. And then, so it's a metric too, so three things. It allows the machine to move over inaccurate features in its own design without causing major disruption of performance of the machine. Almost all machines that have any precision use in manufacturing use preloaded bearings. Remember these modular bearing elements we had? These are preloaded by the way the grooves in the carriage and the grooves in the rail interact with each other via the recirculating rolling elements, or the balls. And the way they do that is that the space between the bearing groove on the rail and the bearing groove on the carriage, the spacing between the two is a little smaller than the size of the ball. So when you put the ball in between the two and load all the balls up, the balls are compressed a little bit, and hence they're inherently preloaded of the carriage to the rail. So you get a very, very stiff structure that's inherently preloaded. Now with rolling element bearings, for rotary motion or linear motion, but we're going to focus here for a minute on rotary motion. Here's images that show what happens to the load supporting region if you have internal clearance in the bearing. Let's see. This was actually from a tapered roller bearing. That if the bearing is not preloaded and you have internal clearance such that it would never be this severe, but that it would move this way, to zero clearance when it just is touching and you're loading it, so just the rollers on the top experience deformation, to with a light preload versus a medium preload, where this red indicates the deformation zone on the rollers. Without any load, the preload, you'd have a uniform red ring around it, and as you apply a load, it's showing that the rollers on the bottom are still partially deformed, and the ones on the top are even more deformed, to provide the same kind of analysis or analogy that we showed with this demonstration. So you have much, much higher total stiffness from your bearing in a radial direction bidirectionally than by applying this little bit of preload than if you didn't. And indeed, these different ways of mounting bearings, the back-to-back mounting, the face-to-face mounting for angular contact bearings, are keys to how high-precision spindles are designed. Even spindles in something like a drill press, when you turn it, boy, that feels real smooth, and I don't feel any rattle in it. These bearings in these machines are also inherently preloaded the way the structures are put together. Now, mounting of your bearings is directly related to whether or not you're going to get proper preload, and also if you're going to overload your bearings or over-constrain them. This figure here shows a very powerful tool for initially doing analysis of the structure by visualizing where the forces go. You want to imagine the forces flowing in, and like water in a river, what path does it go? It looks for the mechanical connection between elements. The force goes in, I'm touching where the ball is, so the force is going to go up into the ball. The ball touches the outside raceway and the force is going to go through it. Pull in the other direction, this orangish arrow, the force is going to go in through this ball. The contacts here, these are the lines of contact. This is what's called a back-to-back bearing. If you think about it, these bearings pushing that way, these bearings pushing that way. The result is where these instant centers meet on the shaft gives you really high stability. By having high stability with this back-to-back configuration, shaft resists moment loads. The total stiffness of the system, for example, I have a spindle shaft for a high-speed, high-accuracy machining center, and I want the spindle to be very accurate and very rigid, so under cutting loads it doesn't deflect. Will be a function of the stiffness of the bearings, the stiffness of the shaft, and the stiffness of the outside housing. Housing, shaft, and bearings form a system that will determine the load, when a load is applied to the end of the shaft, how the whole thing deforms. Again, your mechanics of solids, which people should know really well now from other classes and application here, are the key to enabling you to predict what the total machine is doing. If you can predict what the total machine is doing, you can write the spreadsheet to then lets you play what-if scenarios with the different elements. Taking that thought a little further, we look here at, again, coming back to our favorite expression, shaft. The bearings act like a spring. Spring, the shaft itself has some spring constant, K bearing, which then sits on the spring of the housing. And this is your goal as an engineer, is to be able to estimate what the stiffnesses of these individual elements are, design your machine, predict the performance of what's happening in the machine, such that if I have some force applied to the machine, the total amount of deflection will be less than what the customer requires. Another fine point of bearing mounting for these angular contact bearings is the following. Machines that run and motion that occurs, there will always be some mechanical loss and heat generated. Where does the heat go and what happens? Well, when you have point contact between the bearings and the raceways, and you're generating heat in the bearing, what happens is the heat has to go somewhere, and it's going to go from the point of generation, it's going to follow a path, just the way pouring fluid into a system or putting electrical energy in, there's a resistance path. So if you have a shaft that's supported by ball bearings, or any kind of bearing, and the shaft is spinning, heat is generated between this bearing and raceway here and this bearing and raceway here. This heat runs into the shaft. You put another bearing on it. And when you have an outside structure, the housing, this heat on the outer bearings, and I haven't properly mounted the bearings in terms of axial motion yet, but we will in just a second, goes into the housing. Okay, now the way I've drawn it here, this housing with these bearings, it's not stable. Actually, the thing will slide. Well, you're right. So in reality, we would have some feature in the housing like that, and probably have a clamp plate here. And the shaft, right, would have some feature in it like this. So I'm pushing here, the force flows up through the bearing. If I'm pulling on it, how do I want to mount, where do I want to have the forces flow? Does this bearing back here just float in the housing? What's happening? If I'm pulling in the other direction, well, how do I want to resist forces coming this way? Well, I'm either going to have to put a feature back here in the housing and another feature on the shaft to let the forces flow, or I'm going to have done this type of structure. And then, for example, this is a threaded collar. And how do I preload this system? Are these the balls inherently preloaded in the raceway, the way these linear guides are? Well, let's look at this in terms of how do we address how we want this system to be based on the mounting of the system and the stiffness and the thermal characteristics, the whole system. When you're running a spindle at some reasonable speed and you're generating heat, you can imagine and see that the shaft is generally going to be a smaller mass than the outside housing. It's just smaller. The heat generated at the inner and outer ring, similar. That means that you're going to put the same amount of heat into the inside structure as the outside structure. The inside structure is smaller than the outside structure. This is going to get hotter than this one. This is going to expand more than this one. Your goal is, how do I mechanically allow for this to get bigger than that without resisting it and generating huge loads? If there is a stiff connection between the inside and the outside at the front and the back, and I impose a thermal deformation on the structure, F equals Kx. The structure grows axially, it actually grows radially also. So now I get to the problem of, if these bearings had a structure like this, radially, the inside growing faster than the outside, you'll crush the bearing. Well, recall we talked about angular contact bearings. Which have a structure like this. The way an angular contact bearing works in this back-to-back configuration, it acknowledges the challenges we just talked about here and says, let's use the principle of self-help to give us a high degree of stiffness and also thermal stability. Watch how this magic happens. Here is the housing. And here is the shaft. So this ring pushes the two inner raceways together and holds them. So now this shaft has bidirectional stiffness. The bearings have been made initially such that when they were manufactured and ground, these are made in pairs. There's a little gap here. And as this nut is tightened, that gap closes. That gives me the preload by the balls deforming in the raceways. As this shaft spins, this gets hotter and wants to expand this way, gets hotter and wants to expand that way. When the shaft expands this way, remember these were preloaded together, they're springs, they're relaxed, and this inner ring here will want to migrate in that direction, causing the ball to become loose, because this spacing will grow and the ball can rattle. On the other hand, the shaft expands this way, and this part of the raceway expands that way, causing the gap between the rings to close to crush the ball. The expansion can't, or in a loosening axial direction, cancels the expansion in the radial tightening direction. That's one of the magics of this back-to-back configuration. This is called a thermocentric design. This is one of the really cool things about machine design. It's like a puzzle. It's like playing a video game. You've got to figure out the challenges and how you get from here and there and collect your points and get to that end prize goal of, whee, happiness winning, which means your machines sell and you make money so you can buy cool stuff, like sports equipment, so you can go and ride your bike and have all kinds of happiness. Okay? Very important. All happens by learning and thinking about all the elements in the system, how you can take ouches and turn them into ahs. Now we talk a lot about doing the analysis for these things in terms of using mechanics of solids, writing spreadsheets, and you can get pretty good at characterizing these machines to allow you to move very fast in your design world. Ultimately then, a machine is a very complex assemblage of elements, and you will sometimes want to use what is called finite element analysis, which there's some special courses and topics just in how to do that. And we have some tricks on how you can model these very, very complex bearings with these rolling ball interfaces and develop very fast, quick, easy to use solid models and finite elements for the bearings. And the trick is, if your bearing rail is made of steel, your carriage is made of steel, and now you got the bearing block here, which is, you think is made of steel. But in reality, you go to the catalog and you find out what the stiffness of this thing is, and F equals Kx, if you know the stiffness of it. And what are you going to do next? Well, I need, in this space, when I apply a force, to have this element deflect a known amount. The stiffness, if I know what it is always going to be a function of the modulus of the material. And I can go into my finite element code, my program, and instead of specifying the modulus of steel for this bearing carriage, I start downgrading the modulus of the material. So I run a few finite element experiments to figure out what is the effective modulus of elasticity of the material of the bearing carriage, such that if I apply a load to it, it will deform according to what the catalog says will happen. And then you can build up the rest of the assemblage of the machine. So you would never actually go and try to use the finite element analysis to model all the individual rolling elements in the bearing. That would take an enormous amount of time. So always be looking for these shortcuts based on simple physics. The same is true of misalignment, where I went to calculate the stiffness for the good performance of the machine. I can now assume that I have the bearings in the front of the machine and then another set of bearings in the back of the machine that are not exactly what they're supposed to be. Stiffness of the machine, which is the bearings plus shaft plus housing. Misalignment tolerances, which is, this is what I'm going to set on my drawing for how good the machine should be built, results in a force on the bearings. That force is in addition to the force that's applied by, like the external cutting forces on the machine. That total force the bearing sees from the applied loads plus misalignment loads plus thermal loads is how you predict the lifetime of operation of the bearing. The text has some very nice spreadsheets where it will allow you to calculate the load that is on a shaft, for example, by the bearings being misaligned and radially and actually tilt, and then give you a number for what this force is. In these pretty colors, you can then go and check some of your machine configurations with finite element analysis in the end to verify your assumptions or correct your making a proper model of what the stiffness of the housing was, which is often the most difficult thing to predict. Now, centers of action. Is that like your local hangout where you go for a pickup basketball game? Because that's where all the action is and everything's happening? Yeah, kind of. Remember this from fundamental principles in topic 3. You have this collection of bearings that are springs. So you have a machine supported by springs, and there is a place where if you push, the machine will have uniform displacement with no tilt. You need to consider, when you're designing a machine and placing your bearings, where the center of stiffness is going to be, because you want to place it such that when loads are applied to the machine, either externally or internally from actuators, you're going to minimize the amount of tilt in your machine and hence limit the amount of the magnitude of the Abbe offset or that occurs. Remember this sailboat mast. Well, that's not really moving. Whoa, it's moving a lot up there. So if you're not applying loads through the center of stiffness, there's a good chance that you're causing these tilt errors, which are then amplifying by distance, which may at the end result of where the tool is in the machine causing a lot more motion than you thought of. So beware of just laying out a machine. Let's put a bearing here, let's put a bearing there. Take a step back and think, okay, this is where I think the bearing should go because it looks like it'll package well. Now, bearings together acting together, where's the center of stiffness? Where is the loads being applied to my machine? They aren't exactly aligned. Well, I'll try to move it as close as possible. Okay, they're still not exactly aligned. At least I know where they are. Now I know the loads, the distance to the center of stiffness gives me a moment, and I can predict now the tilt of the machine amplified by that distance. Is that parasitic motion that I'm getting acceptable or not? If it is, you're all set. Hey, more of these fundamental principles are coming back. Mr. St. Venant. Carriage, supported by bearings, moving. Look at the spacing of bearing wide apart. If I apply forces at A, it moves nicely. If I apply forces at B, there's a good chance that this will tilt, and the warning bells go off. No, no, no. Here's this figure we have again from Topic 3, Fundamental Principles. Long to wide. You can put forces anywhere. This is not going to jam. Similarly, for mounting rotary motion bearings, consider here's a wheel, a shaft. Here's just one little bearing in here. Very, very bad. And it's amazing on junior robotics and simple machines, and people have these really clever ideas for what a machine should do, which very clever, and then breaks after a little bit. Oh, that's right, it's details. Details are important. Why not just do it right the first time? Spacing of the bearings, here we are about 4 shaft diameters apart, and the loads are being applied only 1 to 2 shaft diameters from the first bearing. This is a very good design. It's amazing how much good design you can do just by looking and applying fundamental principles. It allows you to lay out the machine such that when you then do go to do the analysis to predict the deformation and loads, you are very close to being just a little bit of tweaking to get it where you need it to be without having to fundamentally redesign things. When you consider all the different ways to mount bearings to achieve the goal of stiffness, load capacity in the direction, thermocentric design, there's no one right way versus wrong way. There's many different alternatives using snap rings, bolted collars, screw-on collars. It all depends upon the type of machine you're designing, the volumes that you're going to be designing them to meet, what modular elements I can buy. This is all part of the puzzle, the video game of design that lets you pick from all these different possible options to bring together and make a machine. Your goal is to do it with a minimal cost, maximum performance. Knowing what options are out there, and then when you close your eyes and you go running or swimming or whatever you do for your creative thought catalyzation, to pick those modular pieces and those nuggets of knowledge and build together a cool machine is absolutely critical. So never stop. Oh, wow. Ooh, wow, there's a new method to designing something. Oh, wow, I didn't think of that one. Pack them in. When we're mounting ball bearings or rotary motion rolling element bearings, this is building more on the thermocentric design discussion we had earlier. And what we want to talk about here is to show a little more on some of the detail or complexity, depending on how you want to look at it, on how you mount your bearings the use of spacers to achieve, with two angular contact bearings, a wider footprint where you can tune your thermocentric design and or your stiffness and load capacity of the bearings. The key, again, is going to be visualizing the flow of forces. Always very important to pretend you're a force and just flow yourself through the machine. Linear bearings are similarly blessed with a plethora of different types of configurations, from simple boxways and dovetails, which we covered a little bit earlier in this lecture, center guidance and flats, round rails, V-ways, V's and flats. Go look at some old machines in the basement, or wherever you keep your old machines, milling machines, lathes. You'll see a lot of these types of bearing rails. Still very useful from sliding contact, or remember we talked about modular aerostatic bearings. You can replace any of these sliding contact bearing configurations with modular aerostatic bearings and now have very high precision, smooth motion, linear motion bearings. As with rotary motion bearings, alignment and the loads caused by misalignment of the bearing rails acting on the stiffness of the bearings, F equals Kx. One of the biggest loads you'll often find in these high-speed automation machines that are moving around is bearings have finite stiffness. They're bolted to frames. They have finite stiffness. And there's misalignment tolerances between things. And now you want to make them move. Those forces add, in addition to the loads that are applied to the machine by the structure they're carrying, to create a limit on the lifetime of that bearing. When you look at a machine next to another machine from vendor A and vendor B, this machine is only $99, wonderful machine. This one is $200, wonderful machine. Why should I buy the $99 machine versus the $200 machine? They're the same thing. Cheap price, let's do it. They both have the same specifications. Yeah. What I like to do is I like to take the covers off and look inside the machine. And I look for keys of how particularly these, for example, the modular bearing rails are attached to the structure. I want to go visit the factory where they make the machines, and as I'm walking through, I'm looking at subtle clues for how do they align their bearing rails. When the carriage is on the structure without anything else attached, just casual conversation, you're walking through and you want to make sure, yeah, that feels real nice. Because once the machine is all bolted together, and there's deformations in it, if it's deforming too much, it won't move so easy. The actuator will force it to move, so it looks like it's going really good, but the loads are higher. Now, these are self-aligning ball bushings in here. And it still moves. It actually still moves pretty smooth. But you see, there's still some force on it. That force of sliding means that there's a high radial force, and the bearings are aligning it, but I really caused a large misalignment of the structure. You can tell by, watch this. See how the structure is misaligned? Let me take that off. It's still somewhat not aligned, but it's not nearly as bad as when the external load was applied, right? So often in the context of just assembling a machine and bolting all the parts together, you can cause enough misalignment to cause the bearings to become overloaded. And that can be the key difference in performance and indeed lifetime between a high quality machine and a machine that's just low cost. And it looks like it's the same machine, but it's actually a very different machine. One may last for years and years, and the other may only last a fraction of a year. So when you're designing your machine, you also should be thinking about designing the manufacturing method for the machine and working with the people on the shop floor for how they're going to take your design intent for the bearings to be placed and to be aligned within a certain tolerance, because you know the stiffness of the bearing. And he's thinking, man, is he going to write that again? Ow! Yeah, because I need you to remember this, otherwise this will happen to you. See this? Parallelism error. Are your bearing rails vertical parallelism, horizontal parallelism? These angular errors in alignment are your toughest thing to battle because they're amplified by distance to cause even larger displacements and larger forces. Beware. A quick example, when you have many linear bearing carriages, perhaps on many rails, for very large machines, how do they average out? And there's a spreadsheet that does that averaging for you based on the stiffnesses of the carriages and the potential misalignments to then come back and predict what the load on each of these bearing carriages is due to the misalignment. So have a look at that spreadsheet and play around a little bit with it to help you start to develop a physical feel for what's the magnitude of the forces and the misalignments we're talking about that can be of consequence. Now start to think about the bearings as a system and how the actuator is coupled to the carriages supported by the bearings. And the most important lesson here is, again, the center of stiffness is a very, very, very important critical element. That the actuator, as it's applying a force and it's having its own motion, is going to have some little parasitics associated with it. Nothing is perfect. And I want those little parasitics, as they're moving along, to be applied through the center of stiffness of the carriage supported by the bearings, such that any parasitic forces that come along are only applied to cause a linear translation of my carriage, not a pitch or roll of my carriage as I move. Very, very important, seemingly subtle, but critical element on how you bolt things together, how you attach one system element to another. Follow the structural loop, look for the centers of stiffness, match them together, and minimize those angular deformations.